Before we ask whether time has a beginning or an end, we must first pause and ask something quieter. What do we mean when we say time? In everyday life, time feels simple. It is the ticking of a clock, the rising and setting of the sun, the slow accumulation of memories. But physics does not define time so gently. In science, time is not a feeling, it is a coordinate, a dimension used to describe change. In classical physics, especially in the work of Isaac Newton, time was assumed to be absolute, universal, flowing at the same rate everywhere in the universe. Newton believed time existed independently of everything else. Even if nothing happened, time would still pass. This idea shaped physics for more than 2 centuries, but it was incomplete because it assumed something profound without proof, that time exists on its own, separate from space, matter, and motion. That assumption would eventually break. Why this question even matters? If time truly exists independently, then asking about its beginning is strange. How can something begin if it already exists to allow beginnings? This leads to our first quiet paradox. To talk about a beginning of time, time must already exist, and yet modern physics suggests otherwise. To understand why, we must slowly let go of our everyday intuition. Stanford Encyclopedia of Philosophy. Time. In 1905, Einstein published a paper that quietly dismantled centuries of assumptions. His theory of special relativity revealed something unsettling. Time does not flow at the same rate for everyone. Clocks tick differently depending on speed, gravity, later shown in general relativity. This was not philosophy, it was experimentally verified. Atomic clocks on airplanes tick differently than those on Earth. GPS satellites must correct for time dilation, or your phone would be wrong by kilometers. Time, it turned out, was not universal. Space-time. Time becomes a dimension. Einstein went further. Time could no longer be separated from space. Together, they form space-time, a 4-dimensional structure where space can bend, time can stretch. Both are shaped by mass and energy. This has a critical implication. If space-time is physical, then time itself may be created, distorted, or destroyed. Time is no longer a background stage. It is part of the universe's architecture, and architectures can have origins. A subtle shift. Before Einstein, the universe existed in time. After Einstein, time exists within the universe. This single shift makes the question of time's beginning scientifically meaningful. References: Einstein on the Electrodynamics of Moving Bodies, 1905. Einstein, General Relativity, 1915. Taylor and Wheeler, Space-Time Physics. Modern cosmology tells us the universe is expanding. If we mathematically reverse this expansion, everything converges toward a state of infinite density, infinite curvature, and zero size. This point is known as the Big Bang singularity. According to general relativity, space-time itself collapses at this point, which leads to a startling conclusion. If space-time collapses, time itself cannot extend beyond it. Stephen Hawking famously said, "Asking what came before the Big Bang is like asking what lies north of the North Pole." In this view, time did not begin inside the universe. Time began with the universe. There was no before. But here is the problem. Singularities signaled the failure of a theory. At the Big Bang, quantum effects dominate. General relativity breaks down. So when physics tells us time began, it is also telling us our equations are no longer trustworthy. This opens the door to deeper questions. Did time truly begin, Or did our current mathematics simply stop working? At very small scales, the universe no longer behaves smoothly. Atoms vibrate, particles fluctuate, reality becomes probabilistic. This is the domain of quantum mechanics. Here, something strange happens to time. Time in quantum theory. In standard quantum mechanics, space is an operator, matter is an operator, energy is an operator, but time is not. Time appears only as an external parameter, a background clock assumed to exist. This is deeply unsettling, because if time is merely assumed, not explained, then quantum theory is incomplete at the deepest level. Physicists noticed a problem when trying to combine quantum mechanics and general relativity. In quantum gravity, the fundamental equation often looks like this: the Wheeler-DeWitt equation. And in this equation, time is missing entirely. This leads to a disturbing idea. At the most fundamental level, the universe may be timeless. What does timeless mean? It does not mean nothing happens. It means the universe exists as a whole. Change is relational, not sequential. Before and after may be emergent illusions. Time, in this view, is not fundamental. It is something that appears when systems interact, like temperature, like pressure. Real, but not basic. Even if time exists, another mystery remains. Why does time move forward and not backward? The laws of physics are mostly time-symmetric. They work the same whether time goes forward or backward. Yet we experience memory of the past, ignorance of the future, aging, decay. This asymmetry is called the arrow of time. Entropy and time. The leading explanation comes from thermodynamics. Entropy is a measure of disorder. The second law states entropy tends to increase. This gives time a direction. But here is the deeper question. Why was entropy low in the past? Why did the universe begin in such an extraordinarily ordered state? Roger Penrose calculated that the probability of such a low entropy beginning is astronomically small, which implies the arrow of time is not explained, it is assumed. A subtle implication. If the arrow of time depends on initial conditions, and if those initial conditions came from the Big Bang, then time's direction may be tied to the universe's birth. Time might not only have a beginning, its flow may also originate there. If time can begin, can it also end? Physics offers several possibilities. Scenario 1, heat death. If the universe expands forever, entropy reaches maximum. No usable energy remains. No meaningful change occurs. Time may still exist mathematically, but nothing happens. This is sometimes called the death of time by boredom. Scenario 2, big crunch. If gravity eventually overcomes expansion, the universe collapses, space-time contracts, time may reverse or terminate. Some equations suggest time could slow, stop, or lose meaning entirely. Scenario 3, eternal inflation. In some models, our universe is just a bubble. Time continues elsewhere. Endings are local, not global. In this view, time never truly ends, it just branches. Physics does not yet tell us whether time must end. What it does suggest is more unsettling. Time may not be a fundamental feature of reality at all. It may be emergent, local, temporary, like a ripple on a deeper, timeless ocean. References: Hawking, A Brief History of Time; Vilenkin, Many Worlds in One; Carroll and Chen, Spontaneous Inflation and the Origin of the Arrow of Time. Some physicists do not merely suggest that time began or will end, they suggest something far more unsettling. Time never existed at all. One of the most serious proponents of this idea is Julian Barbour, a physicist trained in general relativity. The core idea. Barbour argues that the universe is composed of static configurations of matter. Each configuration is complete in itself. There is no objective flow connecting them. He calls these configurations nows. In this view, the universe does not evolve, it simply is. What we call time is a psychological ordering of static states. Motion, change, and history are illusions created by memory. But this is not mysticism. Barber's argument comes from the mathematics of classical and quantum gravity, the structure of configuration space, and the absence of time in fundamental equations. In timeless formulations of physics, the universe is described as a whole, not as something unfolding. Why this matters? If Barber is even partially correct, time does not begin. Time does not end. Time emerges only for subsystems capable of memory. Time would be a feature of observers, not reality itself. Another approach avoids denying time entirely. Instead, it reframes it. This is the relational view, associated with Carlo Rovelli. The relational principle. According to this view, there is no universal clock. Time exists only between systems. Change is defined relative to other changes. A clock does not measure time itself. It measures correlations. Time, then, is not something flowing in the background. It is a bookkeeping tool for relationships. Thermal time hypothesis. Rovelli and collaborators proposed something remarkable. Time emerges from thermodynamics. In systems out of equilibrium, entropy gradients exist. A direction appears. Time becomes meaningful. Without entropy gradients, time loses its direction and possibly its existence. This suggests the beginning of time may coincide with the emergence of entropy differences. The end of time may occur when those differences vanish. Now we arrive at a delicate boundary. Not speculation, but interpretation. Physics describes structure, but time is also experienced. Why does consciousness experience a flowing present? Physics versus experience. Physics contains no now, no privileged present, no built-in flow. Yet the human mind experiences continuity, direction, duration. This gap is not ignored by serious thinkers. Memory creates time. One hypothesis is conservative but powerful. Time is the ordering of records. We experience time because our brains store records of previous states. We compare present inputs with stored information. The illusion of flow emerges. From this perspective, the past exists as records. The future exists as uncertainty. The present is a cognitive construct. If this is correct, the universe does not move through time. Conscious systems carve time out of static reality. Time would not be fundamental to the cosmos, but fundamental to minds. Reference: Dennett and Kinsborn, Time and the Observer. Barber, The Nature of Time. Carroll, Why Do We Remember the Past but Not the Future? Where We Now Stand. At this depth, modern physics offers no single answer, but it does offer constraints. Time may have begun with the universe, or it may emerge from entropy, or it may not exist fundamentally at all. What is increasingly clear is this: time is not what common sense believes it to be. At the deepest level, physics is written in mathematics. So an unavoidable question arises: does mathematics assume time, or can it exist without it? Surprisingly, most fundamental equations do not require time at all. Block universe mathematics. In relativistic physics, space-time is treated as a four-dimensional geometric object. Mathematically, the entire history of the universe exists as a single structure. Past, present, and future are equally real. Change is not something that happens, it is something that is. This is known as the block universe interpretation. In this view, the universe does not evolve. Observers move along world lines. Flow is not a physical variable. Nothing in the equations prefers one slice of spacetime over another. A technical but crucial point: if the laws of physics are written as constraints on the whole spacetime, then time evolution is not fundamental. It is a way observers parameterize correlations. This aligns with general relativity. canonical quantum gravity, covariant path integral formulations, time becomes a label, not an engine. This question is subtle and often misunderstood. If time is not fundamental, how can cause precede effect? Physicists answer carefully. Causality in relativity. In relativity, causality is defined by light cones, not by time flow. An event can influence another only if they are causally connected. Before and after depend on space-time structure. Thus, causality is geometric, not temporal. You do not need a flowing time for causality, you need an ordering relation. Quantum causality. Recent research has gone further. In quantum information theory, physicists study indefinite causal order. In these systems, event A is not strictly before or after event B. Causal structure itself becomes quantum. Experiments have confirmed this behavior in controlled quantum systems. This suggests something radical. Causality may exist without a fixed time order. Time, again, looks emergent. References: Odeshkov, Costa, and Bruckner, 2012. Hardy, Quantum Gravity Computers. Rovelli, Covariant Loop Quantum Gravity. Now we enter the most difficult frontier. Quantum gravity attempts to unify quantum mechanics and general relativity. Here, the problem of time becomes unavoidable. The Wheeler-DeWitt constraint. In canonical quantum gravity, the universe is described by a wave function, but the fundamental equation takes the form h times psi equals 0. There is no time derivative, no evolution parameter. The universe's quantum state is static. This is not interpretation, it is mathematics. What this implies? At the deepest level, the universe does not evolve. Dynamics must be reconstructed internally. Time must emerge from correlations between subsystems. Physicists call this internal time or clock variables. A subsystem behaves like a clock relative to another subsystem. Time is not global. It is local, approximate, and contextual. Loop quantum gravity. In loop quantum gravity, space is quantized. Geometry has discrete spectra. Time does not appear as a fundamental variable. The theory predicts no singularities, possible bounces instead of beginnings, time losing meaning at Planck scales. But again, no fundamental clock. At this depth, something consistent is emerging across independent approaches: general relativity, quantum gravity, thermodynamics, information theory. All suggest time is not a basic ingredient of reality, yet experience insists otherwise. This tension is not resolved, and that unresolved tension is exactly where modern physics currently lives. Modern physics increasingly treats information as fundamental. This raises a precise question. If time is not fundamental, can information still exist? Surprisingly, the answer appears to be yes. Information is not temporal. In physics, information is a relation between states, a constraint on possibilities, a structure, not a process. A written book contains information even if no one reads it. A crystal encodes information in its lattice, even when nothing changes. This suggests information does not require flow, it requires distinguishability. Thus, a timeless universe can still contain information. Quantum states and timeless encoding. The universal wave function in quantum gravity is static, yet it contains correlations, entanglement, structure. Observers embedded inside this structure extract time by comparing subsystems. Time becomes a compression scheme, a way for limited agents to navigate complex information. String theory approaches quantum gravity very differently. Instead of quantizing space-time directly, it replaces particles with extended objects. Time appears, but not in the way we expect. Most formulations of string theory assume a pre-existing space-time. This includes a time dimension, a causal structure, but this is widely regarded as a limitation, not a success. The deeper goal is a background-independent formulation. Emergent time in ADS-CFT. One of the most solid results in string theory is the ADS-CFT correspondence. It shows that a gravitational universe with time can be equivalent to a quantum theory without gravity defined differently. In some formulations, time in the bulk emerges from entanglement patterns. Geometry arises from information. This strongly suggests time may not be fundamental even in string theory. It may emerge from deeper non-temporal degrees of freedom. Van Ramsdonk, building up space-time with quantum entanglement. Now we return to cosmology, but without assuming a beginning. Hartle and Hawking proposed a universe with no initial singularity, no first moment of time, and a smooth transition from space-like to time-like dimensions. In this model, asking what came before is meaningless. Time emerges gradually. There is no edge to time, only a change in geometry. In loop quantum cosmology, the Big Bang is replaced by a bounce. Time exists on both sides. The arrow of time may reverse or re-emerge, but near the bounce, classical time dissolves. Quantum correlations dominate. Again, time becomes approximate, not absolute. Eternal models. Some models suggest the universe has no beginning, but observers always perceive a beginning due to entropy gradients. This creates a deep distinction between global time, possibly infinite or non-existent, experienced time, always finite and directional. At this depth, physics is no longer asking when time began or how it ends. It is asking whether time is real at all, whether reality needs it, whether existence is fundamentally static. And the unsettling consistency across approaches is this: whenever we dig deeper, time fades, but experience does not. That contradiction remains unresolved. If time is not fundamental, something else must replace it. Physics does not allow chaos at the base level. There must still be structure. The key idea here is ordering. Partial orders instead of time. In several modern approaches, reality is organized not by time, but by partial orders. Some events are related, some are unrelated. No global before exists. This is weaker than time, but stronger than randomness. A partial order allows consistency, causality, local sequencing without requiring a universal clock. One serious research program proposes space-time is a discrete set of events ordered by causality. There is no continuous time, no flowing parameter, only a network of can-influence relations. Time emerges when this network becomes dense and smooth at large scales. At the deepest level, the universe is a causally ordered graph. Time is an approximation we infer. References: Bombelli et al., Space-Time as a Causal Set; Sorkin, Causal Sets, Discrete Gravity; Dowker, Introduction to Causal Sets. This is not philosophical wordplay. It is a technical issue. Laws are usually written as evolution equations, but if time is absent, what are laws? From laws to constraints. In timeless physics, laws do not describe change. They describe allowed structures. Instead of saying, this state evolves into that state, the theory says, only these configurations are permitted. Reality becomes a static solution space. What we call dynamics is movement within this space by observers. A key shift. This reframes physics from predicting the future to describing consistency. The universe does not run like a program. It satisfies a set of conditions. Reference notes: Dirac, Lectures on Quantum Mechanics; Barber and Foster, Constraints and Timelessness; Smolin, The Trouble with Physics, A Critical Perspective. At this depth, the problem is no longer cosmological, it is explanatory. If time is not fundamental, why is the illusion so strong? Robust illusions. Physics recognizes something important. Some illusions are not errors, they are stable features. Temperature is an illusion. So is pressure. So is solidity. They emerge reliably from deeper laws. Time may belong to this category. Why the illusion persists. Time feels real because entropy gradients are stable. Memory formation is irreversible. Conscious systems are dissipative. We are thermodynamic structures. As long as entropy increases locally, time will appear to flow. This is not subjective fantasy, it is physical necessity. Probability usually assumes repeated trials, temporal sequences, outcomes unfolding in time. But if time is not fundamental, this framework collapses. Yet quantum physics is irreducibly probabilistic. So the question becomes precise. What is probability if nothing happens over time? Probability as measure, not process. In timeless physics, probability is not about evolution. It is about measure over configuration space. Think carefully here. Instead of asking, what will happen next, physics asks, which configurations exist and how are they weighted? Probability becomes static. It describes how much of reality looks one way versus another way, not how reality changes. Born rule without time. In quantum gravity, the Born rule is interpreted as a rule assigning weights to correlations, not outcomes in a sequence. Observers embedded in a static wave function interpret these weights as temporal uncertainty. Time enters through self-location uncertainty, not evolution. Reference notes: Hartlow, Quantum Mechanics of Individual Systems; Page and Wooters, Evolution Without Evolution; Wallace, The Emergent Multiverse. The word now feels unavoidable, but physics is merciless here. No preferred present. Relativity proves there is no global present. Different observers disagree on simultaneity. No slicing of spacetime is privileged. This is not interpretation, it is experimentally verified. Thus, there is no objective now in the universe. Local now as a physical process. However, physics does allow something weaker. A local now emerges when information arrives, memory is updated, a system synchronizes internally. This present is local, finite, and observer-dependent. It has no cosmic significance. Any theory that postulates a universal present, a flowing now, is incompatible with relativity. This sharply constrains metaphysical interpretations. Now we approach your original question, but without answering it. If time is emergent, the phrase "end of time" becomes ambiguous. Three distinct meanings. Physicists distinguish physical processes, end of entropy gradients, breakdown of time as a useful description. Only the third is fundamental. When time ceases to make sense. At extreme conditions, near singularities, at Planck scales, in quantum gravity regimes, time ceases to be definable. This is not an event in time, it is the failure of time as a concept. So asking, what happens after time ends, is like asking, what is north of the North Pole? The grammar fails. Time increasingly looks like a coordination tool for limited subsystems inside a static or relational whole. But experience still resists this picture. That resistance is not dismissed, it is part of the problem. Computation seems to require steps, sequences, before and after. So if time is not fundamental, how can anything compute? This is not abstract. Physics increasingly treats the universe as information processing. Computation as logical structure. In its most abstract form, computation is not a process. It is a mapping between input and output states. A logic gate does not need time conceptually. Time is only required when a physical system implements it. In timeless physics, the entire computation exists as a static structure. Different stages coexist as relations, and observers moving along correlations interpret this as execution. Path integral perspective. In quantum field theory, path integrals sum over entire histories at once. Nothing runs. all paths exist in parallel as a weighted structure. Time ordering emerges only when we condition on partial information. Thus, computation can exist as a static relation, not a temporal process. Reference notes: Feynman and Hibbs, Quantum Mechanics and Path Integrals. Lloyd, Ultimate Physical Limits to Computation. Aronson, Quantum Computing since Democritus. Earlier, we softened causation into ordering. Now we sharpen it. Counterfactual causation. Causation is often defined as, if A had not occurred, B would not have occurred. But this does not require time. It requires dependency. Physics increasingly defines causation as constraint satisfaction, information flow, correlation under intervention. None of these strictly require temporal flow. Quantum causal models. Modern research uses causal diagrams that do not assume time order, allow cyclic dependencies, allow indefinite causal structure. These models are predictive and testable. They replace temporal intuition with algebraic consistency. Now we confront a subtle danger. Even physicists who deny fundamental time still speak temporally. Is this a flaw? Language versus ontology. Human language evolved for action, prediction, survival. It is deeply temporal. Physics, however, is not obligated to respect linguistic intuition. The equations themselves contain no tense, contain no now, contain no flow. Temporal language is a translation layer, not reality. A hard limit. This creates an unavoidable asymmetry. Reality may be timeless. Description by embedded agents may never be. This is not confusion, it is a structural limitation of self-referential systems. Entropy is often treated as the engine of time, but this may be backward. Entropy without temporal flow. Entropy is a property of a state, not a process. A configuration can be high entropy, low entropy, without anything happening. In statistical mechanics, entropy is defined over phase space, a measure of how many microstates correspond to a macrostate. No time variable is required. Thus, entropy does not require time. Time enters only when we compare records of states. Entropy gradients as the source of time. What we experience as time's direction arises when a subsystem sits in a low entropy configuration surrounded by higher entropy possibilities. This asymmetry creates memory, irreversibility, and apparent flow, but the gradient itself can be static. The universe does not need to evolve to contain entropy differences. If the universe is timeless or block-like, a troubling question arises. Is anything genuinely new, or is novelty an illusion? The block objection. In a block universe, all events coexist. Nothing comes into being, nothing passes away. This seems to eliminate creativity, freedom, and emergence, but this is too fast. Novelty as internal differentiation. Even in a static structure, different regions encode different information. Correlations differ. Local perspectives are limited. For an embedded observer, encountering a new correlation is indistinguishable from novelty. Novelty does not require creation. It requires inaccessibility until correlation occurs. Reference notes: Anderson, More is Different; Dennett, Freedom Evolves; Tegmark, Life 3.0, Restricted Use. Now we reach a subtle fracture. If time is not fundamental, what does it mean to be the same thing? Identity is usually temporal. We assume identity means persistence through time, continuity of existence. But if time dissolves, this definition fails. Identity as structural continuity. In physics, identity is replaced by pattern preservation, correlation stability, functional equivalence. An electron is the same, not because it persists, but because it satisfies the same constraints everywhere. For complex systems, identity becomes approximate, context-dependent, emergent. The self is not a thing, it is a pattern traced across correlations. Implication: if time ends or never existed, identity does not vanish, it redefines itself non-temporally. Free will seems inseparable from time. Deliberation, decision, action all appear sequential. So if time is not fundamental, does choice disappear? Physics answers cautiously. Free will as constraint satisfaction. In contemporary physics and philosophy, free will is no longer defined as the ability to change the future. Instead, it is increasingly defined as the ability of a system to act according to its internal structure. This does not require time. A system exhibits agency if its behavior depends on internal states. Those states encode goals, memories, or preferences. Outputs are sensitive to information. All of this can exist as a static relational structure. Block universe compatibility. In a block universe, choices are not created, they are encoded. But from inside the block, deliberation still occurs, uncertainty still exists, responsibility still functions. This is not illusion, it is indexical limitation. If time is emergent, what about laws? Do laws govern reality or merely describe it? Timeless laws as geometric constraints. At the deepest level, laws appear as symmetries, conservation principles, mathematical invariances. None of these evolve. They are not instructions, they are conditions. Reality does not follow laws, it satisfies them. Why this matters? If laws are timeless, they cannot act, they cannot cause, they cannot change. They are closer to geometry than command. This dissolves the idea of a universe running in time. Now we reach something precise. The word beginning presupposes a temporal ordering, a before and after. But if time is emergent, then the question, did time have a beginning, may be malformed. Category errors in physics. Physics has encountered this before. Examples: asking for the location of a wave function, asking for the temperature of a single molecule, asking for the velocity of space-time. These are not unanswered questions, they are ill-posed ones. In several modern frameworks, the universe does not begin in time. Time begins in the universe, which means beginning applies to time, but not temporally. It is a structural emergence, not an event. Where we are now, still unresolved. At this depth, choice survives without temporal creation. Laws persist without governance. Beginnings dissolve as category errors. Time is almost entirely absent, yet explanation has not collapsed. What remains unexplained is experience itself. That problem is still ahead. Physics can describe structure without time, but experience appears stubbornly temporal. This raises a reversal of the usual question. Is time a condition for experience, or is experience the condition for time? Minimal requirements for experience. From neuroscience and physics combined, experience appears to require information integration, memory, records of correlation, and irreversibility, thermodynamic cost. None of these require fundamental time. They require asymmetry, constraint, dissipation. Time may be a byproduct, not a prerequisite. Experience as ordered correlation. An experiencing system does not need flowing time. It needs distinguishable internal states, a rule for relating them, and limited access to the whole structure. Experience is the local traversal of correlations. Traversal is not motion, it is conditional access. Reference notes. Tononi, Integrated Information Theory, limited scope. Friston, Free Energy Principle. Seth, Being You. Physics denies a global present, yet consciousness insists on one. This is not contradiction, it is compression. The present as an interface. The brain is not a passive observer, it is a prediction engine. To function, it compresses past records, future expectations, and incoming sensory data into a narrow window. That window is what we call now. why the illusion cannot be removed. A conscious system that did not experience a present would fail to coordinate action, fail to learn, fail to survive. Thus, any system capable of asking about time must experience a now. This is not metaphysics, it is selection. Now we confront a hard boundary. Physics removes time again and again at the fundamental level, but it keeps reappearing in observation, in thermodynamics, in explanation. This suggests something precise. Time may be eliminable from ontology, but not from epistemology. Explanation requires order. To explain anything, we must condition on information, compare possibilities, use asymmetry. Explanation itself is a temporal act. Even if reality is timeless, understanding it may never be. This is not failure. Physics does not aim to erase experience. It aims to constrain what is fundamental. Time may be like perspective in geometry, coordinates in relativity, gauge choices in field theory, removable from equations, unavoidable in use. Where we are now, still no end. At this depth, experience does not require fundamental time, but explanation may. Physics can remove time from equations, but not from inquiry. Time may be not a thing, not an illusion, but a mode of access. That is not a conclusion. It is a boundary. At the deepest level reached so far, something subtle has happened. The question, can time have a beginning or an end, has slowly transformed, not into an answer, but into a realization about what kinds of questions physics can ask. Physics is powerful, but it has limits. It can describe structure, it can constrain possibilities, it can eliminate unnecessary assumptions, but it cannot always preserve the grammar of everyday language. When time is no longer fundamental, words like beginning, ending, before, after lose their footing. They are not wrong, they are scale-dependent. Just as solid disappears at the atomic level, beginning may disappear at the deepest level of reality. So what can we say without exaggeration? Physics suggests that time behaves like a fundamental ingredient at human scales. It becomes flexible at relativistic scales. It fades at quantum gravitational scales. This is not a contradiction. It is layered reality. At no point does physics prove that time is unreal. It only shows that time is not always required. And something important follows from this. If time is emergent, it can appear, disappear, and reappear, depending on scale. In that sense, time may not have a single beginning, nor a single end. It may have domains of validity. We can now restate the original question in a gentler form. Not, did time begin? Not, will time end? But, where does time apply and where does it stop being useful? In everyday life, time works. In astronomy, it bends. In black holes, it fractures. At the Planck scale, it dissolves. And beyond that point, physics does not rush to replace it. It simply becomes quiet. Wald, General Relativity. For a channel like the Wandering Neuron, for an audience that prefers depth over drama, this is the most honest ending physics can offer. Time is not a single thing. It is a tool, a description, a perspective, a consequence of complexity. At some levels, it is indispensable. At others, it quietly steps aside. And when it does, nothing catastrophic happens. Reality continues, even if the word continue no longer applies. A slow goodbye. If you are listening to this as sleep content, there is nothing left to solve tonight. Physics has not closed the question, but it has softened it. And sometimes the most accurate understanding is knowing where understanding naturally comes to rest. You don't need to follow time any further. It will be there when you wake. Final reference cluster. Einstein, 1905-1915. Hawking and Ellis, Penrose, Ravelli, Barber, Carroll, Wald.